Okay, so welcome everyone to the second session of this moduli space of curves mini course. So yesterday we had a look at the definition of MGN and MGN bar. So let us recall the first one is the moduli space. So it's the space parametrizing smooth curves of genus G with n mark points. And we saw that the n mark points had to be distinct and labeled. So I know which one is the first one, the second one, and so on. And this is going to be important today. And then we also saw that this space has dimension 3G minus 3 plus n, if you remember, because what I can do is I can take a loop, a B cycle around one of the holes of the surface, and I can start degenerating this cycle until I pinch it. And as I pinch it, I create a node. So it's a self-intersection of the kinetic component. And so first of all, the entire family is smooth, but its limit is not, and therefore the space is not compact. And also, every time I do so, I lose one dimension. We saw that we lose one real dimension, but in fact, we lose one complex dimension because of something that we didn't go through that is called Weil-Peterson coordinates and Weil-Peterson volumes. But the main point is that you would have, when you have such a cycle, you could reconstruct the hyperbolic metric on the surface by cutting and gluing. But when you glue, you both have the coordinate that is relative to the length of the cycle and the coordinate that is relative to the angle of gluing. So in fact, you're losing two real dimensions that account for one complex dimension. And so yesterday I tried to convince you of the fact that the number of such loops that you can find in a surface of genus G with n mark points, thinking of the mark points as boundaries, when you decompose the surface in pair of pants, that's exactly the dimension, because after you looked for all of these possible loops and you degenerated each of them, you find components which are only of genus 0 with 3 mark points. And so those are parameterized by the space M03 that, if you believe me, has, well, we'll see it today, has dimension 0. So now you decompose your surface in something that has in pieces that have dimension 0, so no dimension. And therefore, if you count how many you have, you take the product of all of these moduli spaces, which are just a point. So finitely many points in the product just give you a single point. So you have no dimension there, and the number of dimensions that you lost, it was exactly the number of loops that we shrunk, and that number of loops is the number of loops you need to decompose the surface into pair of pants. And by induction, you can prove that is 3G minus 3 plus n. And also we saw that number of pair of pants, which is not number of boundaries, it's almost 2/3 of that, because every pair of pants has 3 boundaries, but each of the boundaries is shared between 2 pair of pants, except if they are mark points. So with this trick, you can see that the pair of pants is 2G minus 2 plus n, which is coherent with the fact that 2G minus 2 plus n is minus the Euler characteristic of the surface. And we also saw that there is a link between the number of automorphisms of the surface and the Euler characteristic. Connected component has finitely many automorphisms if and only if the Euler characteristic is negative. And when we take the compactification, we need only finitely many automorphisms everywhere, because we want this orbifold structure that in the definition has these finite groups. That's when we get this Deligne-Mumford stack that is comfortable for computations, because we know how to control better its intersection theory and its fundamental class and so on. And therefore, the moduli space of stable maps can contain all possible connected components except the ones that have non-negative Euler characteristic. And we saw that there are only 4 bad cases, and the 4 bad cases are the torus without mark points and the sphere with 0, 1, and 2 mark points. So those are the 4 bad cases you never want in the compactification MGM bar. It's a Riemann-Mumford compactification. For the rest, you can have all the components that you want, and you only insert the non-smooth surfaces which have no dot singularities. So that's the summary of the 2 hours of yesterday. And then we saw the stratification of MGM bar, and we computed in some examples, and some examples are given as exercise. Okay, so this was the 5 minutes intensive summary of the last episode. And today we see some examples of moduli spaces. So let me first go through some examples in genus 0. And if you look at genus 0, we know that every simply connected compact Riemann surface is isomorphic to CP1. CP1, I mean the Riemann sphere, or I mean, it's just basically the complex numbers, and then you compactify them with 1 point at infinity. So you can think of this as taking the complex numbers and you just wrap them up around the ball, and you're missing the North Pole, and the North Pole is your infinity point. And so in every direction you go to infinity, you will end up at the same point, infinity. And we also know what is the automorphism group of CP1. The automorphism group of CP1, as you probably heard before, is given by these transformations, which are called the Möbius transformations. And they're very simple transformations. Basically, you take your complex variable z, and you send it to az plus b divided by cz plus d. So these are global degree 0 transformation as a rational function in z, which are given by the ratio of 2 degree 1, so just linear functions in z, az plus b divided by cz plus d. And you also want that the determinant of the matrix given by a, b, c, d is not 0. So you have 4 parameters, but now you take the projectivized version of that, so you actually have 3. And you are discarding some codimension 0 thing given by the fact that the metric is degenerate. So the group you end up with is PSL2C. Actually, I think you want the determinant to be 1. Yeah, maybe it's not so important for now. Anyways, so you have this group of transformations, which is, of course, infinite. And so you're not happy because we said yesterday that we want only finite automorphism groups. And so we have 3 complex dimensions now, and now we are going to kill them so that we have something on dimension 0, and then we will be happy because we have a finite group. And so there is this standard proposition in complex geometry that says that every time you fix 3 points on CP1, and then you also fix 3 points as the values, as the images of these points through some Möbius transformation that you like, then the map is unique. If you remember, there is this, I don't know how it is called internationally, but I teach linear algebra to IDIL and environmental engineers. And we do this theorem that is called the structure theorem for linear applications, for linear maps. I don't know if it has the same name abroad, but because I teach in Italian. But the point is that if you fix a vector space and then you take a basis, and then the basis has a certain cardinality, n, that is the dimension of the space, of course, and now you're fixing the images of the basis vectors, then there is exactly one. So it exists and is unique, a linear mapping that sends the vector of your basis to the images that you fixed, and then you can just define the mapping by extending by linearity to all other vectors. You just take a vector, you say, okay, this is a linear combination of the bases, and because my linear mapping is linear by definition, then I just define it as the same linear combination that it had in the domain, but now I would take the same linear combination with the same coefficients, but in terms of the images of this basis of these basis vectors. And so basically, once you send the basic vectors, you're done. No? They determine everything uniquely, and the solution exists and is unique. So it's very rigid in some sense. And if you want here, exactly the same is happening. Not maybe exactly the same, but it's the same principle applies, let's say. So you have an automorphism group of dimension 3, but now you're fixing 3 points in the domain and 3 points in the codomain, which is the same, but in the image. And now you can say that there exists a unique some linear mapping. No, not linear mapping, that Möbius transformation that sends the first point where you want, the second point where you want, and the third point where you want. And it's customary to pick these points as 0, 1, and infinity. I mean, you could pick any 3 points you want, but somehow 0, 1, and infinity are usually taken to be the standard ones. So why not going with the tradition? And so now if you have 3 fixed points and you want to send them exactly there, you can convince yourself that when you consider M03, M03 is the moduli space parameterizing rational curves with 3 mark points. Now you can just take P1 and P2 and P3 as those mark points. And now you say, well, that I know that there exists a unique Möbius transformation that is sending them to 0, 1, and infinity. And this is a bialomorphism. This is an element of the automorphism group, so it's invertible. And so since we are considering the moduli space curves up to isomorphisms, now you can say that every single genus 0, 3 mark points curve is completely equivalent to the rational curve with a mark points 0, 1, and infinity. And that's basically, it means that the moduli space M03 only has 1 point. Because you can take the point with 0, 1, and infinity as mark points as a representative of your equivalence class, and you just prove that you can always go to that representative with a bialomorphism. So they're all equivalent to that one, and therefore M03 is just a point. So if you like, the ones that have fewer mark points, so 0 mark points, 1 mark points, and 2 mark points, they are also points, but the stabilizer of those spaces is some automorphism group that is infinite. And so you don't like that for the Riemann compactification. You still have a point, but now you have like a 3 minus n dimensional group that is acting on it. Whereas if you consider M03, you just have a point and you have the trivial group that is acting on it because you exhausted all the dimension of the automorphism group you had by killing it by fixing points. So every time you fix a point, you add a codimension 1 condition on your space, and you just added exactly the number of points equal to the dimension that you needed to kill. So that's the trick, basically. And since M03 is the point is already compact. So when you compactify M03, you still get the point. So basically, there is no advantage in compactifying M03. It's just exactly what you had before. Okay. So okay, so I just wanted to
I think you mute yourself. Okay.
Oh, is it okay now?
Yes.
So let me go through the case in which we add a few more mark points now. So let me imagine that now we have 4 mark points, and as because of the proposition that we just saw, you can take always the first 3 mark points. You know which ones are the first 3 because let me remind you that they are labeled, so you can always take which one is 1, 2, 3. So those ones you can put them in the position 0, 1, and infinity through a bialomorphism. And the fourth one is completely determined because the bialomorphism exists and is unique. So it will go somewhere. You don't know where, but it's forced by the images of the other ones. And so now you have this fourth point that we can call T. And since all the points are distinct, then this T will be an element of P1, of CP1, the Riemann sphere, but it cannot be either 0, 1, and infinity. So basically now, by the position of this point, imagine that this fourth point now is going around all possible points of CP1, but avoiding 0, 1, and infinity. And now you have exactly one equivalence class up to biolomorphisms that is parametrized by this T. So this fourth point is parametrized in the whole space. That's what I'm trying to say. Because every curve would have the first 3 points in 0, 1, and infinity, and the fourth one will be somewhere. But that position will identify the equivalence class. So now you can exploit this trick to take the fourth point. Imagine that the fourth point is going around the space, and you say, aha, this point is now parametrizing my whole space. So I now can compute M04 through this point that is roaming around. And so now M04 will be itself CP1 minus 3 points. Okay. And since I have something that is almost compact, I mean, I'm just missing 3 points. Now when I compactify the space, I get CP1. So M04 is CP1, M04 bar, sorry. And M04 without a bar is just missing 3 points. And so now we can just check that our formula works, the formula for the dimension. If we take the formula for the dimension, that is 3g minus 3 plus n, okay? So the genus is 0, so you get 0 minus 3 plus 4. 4 minus 3 is 1, and CP1 has dimension 1, so we're golden. The dimension matches. Then we can also ask ourselves, wait a second, we compactify the space by adding 3 points, so these 3 points must be equivalence classes of singular curves. We must have some singular curves that in exactly three strata, and those singular curves must be the curves that we added, because we saw yesterday that the Riemann for compactification exactly adds the nodal curves. Okay, but with 4 mark points, what can we have? Well, because we are in dimension 1, let me remind you that every node, or equivalently every edge, introduces one codimension in the locus of curves. So now, since we are in dimension 1, we can only allow ourselves a single node or a single edge in the dual graphs. Okay? And now we have to only consider, since we're in genus 0, all the components will be rational. So again, genus 0. And now we just have to distribute the 4 points in all possible ways, but keeping in mind stability. We cannot break stability. So we have to ensure that every component has at least 3 special points. Otherwise, we break the automorphism requirement. So what can I do? I can take 2 rational curves attached by a node, and I now can distribute the points 1, 2 on this component and 3, 4 on this component. So let's check. If I consider the rational component on the left, it would have indeed 3 special points. 2 are marked points, and 1 is a node. And if I consider this component, also will have 3 and 4 as marked points and a node as additional special points. So this is parameterized by M03, and this is parameterized by M03, and everything is stable. Okay, so now I'm happy, and it's just a matter of combinatorics. I just have to deal with all possible ways of distributing 4 points in all possible on these 2 components, right? But in fact, if you swap 1 and 3 and you swap 2 and 4, you just get the same graph. You don't get a different one. I mean, because you have this, you will just get 2 rational components attached by a node with exactly the same labeling. So you cannot play this game. You cannot you cannot swap 1 and 3 and 2 and 4 and expect that you get something different. But what you can do is to swap them in cross order. So for example, if you just swap 2 and 3, you will get something different, because you see here in the same component, 1 and 2 are in the same component, but now 1 and 3 are in the same component. So these 2 are different. And there is the last one that you can play with, is when you swap 1 and 4. Okay, so now, sorry, when you swap 2 and 4. So now 1 and 4 will be together, and 2 and 3 will be together. You can try, all other combinations are covered this way. Of course, you cannot swap 1 and 2 and pretend that they are a different locus, because they're still roaming around in the same component. Okay, So these are exactly the 3 points that we are missing on M04, and we need to add. So add these nodal curves to get a compacted Fourier version. So everything matches up, and it's very explicit. And the next question you could ask is which one of these 3 points corresponds to 0, which one corresponds to 1, and which one corresponds to infinity. And there is a way to do that with t. There's a little limit that you can take with t. And this is explained in the notes of Dimitri Tzwonkin. So if you want more details, you can just look at it. But now you also know how to deal with M0n in general for n that is larger than 4. Because the trick is going to be very easy, no? You just take the space of all of these, the first 3 points, you want to send them to canonical points, like 0, 1, and infinity. And now you're left with n minus 3 points. So let me call them z4, z5 up to zn. These are points in C to the power n minus 3. And you know that they should be distinct in the image. So they should be distinct among themselves, and also they should not be equal to 0, 1, and infinity, because those points are taken. So that now you can, this is the description of M0n without a bar, and now you can count how many points you're missing for it to be points or strata that are missing for the space to be compact. So for example, if you take M05, this is going to be two-dimensional, and there is a description in Enard's book that is called Counting Surfaces. So it's a beautiful book that I highly recommend. And the book itself is on topological recursion, but there is a chapter on modular space of curves. And here you have in pages 247, 249, you find a description of M05 as CP1 times CP1. But in fact, when you compactify it, you add some strata of, you take the union with some copies of C that have dimension 1. So you will see that you have strata that are not of the same dimension. And in fact, you also have a description as a blow-up that you would find on the Tzwonkin notes. Okay. So actually, the limiting trick is here. How does it happen that M04 bar minus M04 have those boundary strata as missing points? And now actually you can take this family of curves depending on t, and you take the points 0, 1, infinity, and t as x1, x2, x3, x4. And now you can take the limit when t goes to 0, for example. So now you're letting this point, the x4 and the x1, you're letting them collide, right? So x1 and x4 are colliding here. But of course, you're in the projective. So, I mean, what you can do is just reparameterize. You can just send x to x over t. And with this trick, you will see that t divided by t is now 1. Infinity divided by t is still infinity. 1 divided by t is 1 over t. And 0 divided by infinity by t is just 0. But now when you're taking this limit and t goes to 0, what happens is that this one is going to infinity. So now x2 and x3 are colliding. So in this parameterization, x1 and x4 are colliding, and in this parameterization, x2 and x3 are colliding. So who is right? The first limit or the second limit? And the answer is, of course, that they're both right, because if 1 and 4 are colliding or 2 and 3 are colliding, it's as if they are closer and closer and they bubble up together. So and they bubble up together, and you have this node in between the components, and it doesn't matter which parameterization you're taking, of course. It should be independent on a parameterization, but the answer is symmetric in the limits. So then you know that this particular limit corresponds to this particular stratum, and now you can play the same game with the other two as an exercise and see who corresponds to this stratum and to this stratum, for example. So you can really compute explicitly. Okay, So now we saw several results about genus 0. Let us see some results on genus 1. So concerning genus 1, by the uniformization theorem, you know that every Riemann surface on a torus is obtained as a quotient of a lattice. So what do? You take the complex numbers and you quotient out by a lattice that is isomorphic to z to the power 2. So you just have a lattice on C. And this lattice, you can always rotate it a little bit in such a way that you have two generators, of course, but one of the generators, you can always normalize it to 1. And the other generators, you normalize it to what is usually referred to as tau, like this. This tau is free to roam around C, provided it's, of course, not linearly dependent on 1, on the other generator that is placed in the point 1. And so depending on this tau, this will determine a lattice and you'll get an elliptic curve because now you're quotient out by a lattice, which means, I mean, the lattice will give you some tile that will tessellate C, the complex plane. And this tile may be, for example, a square or maybe 60 degrees or maybe any other tile actually. So it would be just an arbitrary parallelogram. And this parallelogram would just tessellate the entire complex plane. But depending on the angle of the parallelogram, you will get a different differential structure on the elliptic curve. So you will always get the equation of the form up to a reparametrization of the form of y squared equal to x to the power 3 plus ax plus b. But somehow like the angle of this tile, this tau will determine a and b through this Weierstrass functions, basically. And you always have this y going to minus y, as we saw yesterday. This is an automorphism of this equation because, of course, if you send one y to minus y, you're not changing y squared. And that's an involution. If you do it again, it's the identity. So you always have a z over 2z group acting on each elliptic curve. So the generic point in this moduli space is what is called the gerb, in the sense that a generic point has non-trivial automorphisms. Whereas in M0n, the trivial point, I mean, a generic point will have trivial automorphism group. But here's not the case. In genus 1, it's not the case. And also an elliptic curve given by the quotient of C by some lattice would be isomorphic to another elliptic curve given by C divided by a different lattice, on if and only if these lattices are proportional by a non-zero scalar of C without the zero. So now you can basically take M11, which is this moduli space of genus 1 curves, so elliptic curves, with one mark point that you can think of. You can think of this one mark point as the neutral element of the group structure. These elliptic curves with one mark point, you can express them in terms of, C divided by some lattice. And as we said before, this lattice is generated by two guys. And one, you can always normalize it to 1. So you can always write it as 1 times z, direct sum tau times z. And then you want to mod out by a group that is taking into account this relation, because you want to remember M11 is those guys, but up to isomorphisms. So now the isomorphisms are given by the proportionality in the complex numbers, and this is encoded by SL2. And you also want that the image of tau is positive because you can always take the fundamental domain and find a representative in the positive, not to overcount. And so now you end up with this picture that you've probably seen before many times. If you are in the complex plane, then you only take the upper half plane where tau roams, and now you want moreover to divide. Sometimes you have taus which roam around, but they are connected by an SL2 transformation, and so you only want to count them once. You only want to take the fundamental domain of this action. And so you don't get the full You don't get the full complex upper half plane, but you only get like a smaller region. And the smaller region is identified by this vertical line that is at x equal to minus 1/2, and this vertical line that sits at x equal to plus 1/2. And then you have this circle with radius 1. And so now the fundamental domain of this action is just this area over here that is shaded, whereas you are quotienting out the line on the left and the line on the right. You want to identify them. And moreover, you want to identify this piece over here of the circle and this piece of the circle, but in different order. So you want like the points that are immediately to the right and to the left to be identified, and eventually this point over here and this point over here to be identified. So here is direct and here is inverse, as the arrows suggest. And in fact, every generic point in here will just be a generic elliptic curve. So we'll have this Z/2Z automorphism group that is finite, but is not trivial. And then you have two special points, this point over here and this point over here. They will correspond to these parallelogram tiles with 60 degrees and 90 degrees. So this will be the square tile, and this will be the 60-degree tile. And they have more automorphisms. So this one has a group of Z/4Z, and this one has a Z/6Z. So there are some special points that have a little bit more automorphisms. And after you take the topological quotient along these lines, you end up with sort of a charisma sock with two special points. You have here the Z/4Z and here the Z/6Z. And well, just have this sock, and it's open now because you go to infinity here. And this is exactly the point that you miss in the compactification, in the open part to get the compactification. And so this point over here is just M11 bar minus M11 open. And this is the only elliptic curve that is not smooth, and it's nodal. And so you'll get what some people call the croissant, as in you're getting this elliptic curve that, of course, as usual, you just took a loop on a B cycle of the surface, and then you just shrunk it to a point. This became a node, and this is given by the equation y squared equal to x to the power 3. And of course, you can check that the discriminant, which is 4 times a cubed plus 27 times b squared is 0 here, because a and b are 0. No, a is, sorry. Yes, they are both 0. So this is the only point that you should add to M11 to get M11 bar. But of course, it's the only stable thing you could do. Like this was very easy to see from our exercises of yesterday. Since you don't have mark points, every time you do something else or you shrink more, you will end up with something that is not stable. Okay, so let us have a look at maps that are natural in this space. Those are called topological maps. And those are very, very useful to define also cohomological field theories. So last time we have seen that MGN bar, you can see it as this joint union, in fact, of this strata. This strata that correspond to some graphs. So let gamma be, as yesterday, a dual stable graph. So these guys over here, if you remember, the recipe was that every component of genus something corresponds to a vertex of that genus. These mark points, you remember them as leaves. Each of the nodes will become an edge, okay? And the total genus, arithmetic genus of this thing is given by the sum of all the arithmetic genus of the labels of the vertices. And moreover, you need to sum up the genus of the graph. So here you have genus 1 for the graph, and plus 2 and plus 1. So 2 plus 1 plus 1 is 4. And this is in fact in M4 with 3 mark points. So M4, 3 bar. Okay. Now we also saw that each of these components is parametrized by smaller moduli space, smaller in terms of larger Euler characteristic of the generic point. Okay, so now you can see mg and bar as the union of all of these strata for each gamma of genus G and N leaves. You just consider this stratum of curves, and this is your stratification. And in fact, what is delta gamma? Delta gamma, you can write it down as 1 over the automorphism of gamma, which is a finite number, as we saw yesterday, by definition. And we computed many of them. And now, basically, every time you see a vertex that corresponds to a component, and you want to take the product with that particular moduli space. So, for example, this stratum will correspond to 1 over 1 because you don't have, I don't think, yeah, you don't have any automorphisms here. And then you will get like the product of n23 bar times m03 bar, which is just a point. So you can sort of ignore this, and m13 bar. So basically the locus of curves with this topology is parameterized by m23 bar times m13 bar. And now the dimension of this delta, what is it? Well, it's very simple because it's just a product of these moduli spaces, which are smaller than the ones we're dealing with. And so, I mean, we can just use the general formula. General formula is 3 times the genus minus 3 plus the number of mark points. So in this case, the genus is the label of the vertex or the genus of the component. So it's 3 times the genus of the component minus 3 plus the number of mark points. But the mark points, as we saw yesterday, are subdivided into 2 categories, the leaves and the half edges of an edge. So for example, this component over here will have P2 as a special point and 2 nodes. And I have to count for all of them. So that's why I wrote it here in 2 different categories, like the half edges of an edge and leaves. And now if I take this guy and I sum all of these contributions up, I get 3 times the genus minus 3 times the h1 of the graph, or the first Betti number, which means how many loops do I have in the graph. So it's just a combinatorial thingy, or topological thingy. And then I have minus 3 times the cardinality of the space of vertices, of the set of vertices, minus cardinality of the set of edges. Again, minus 1 time this guy plus n, because the cardinality of the set of leaves when I sum over all vertices will be all of the mark points, and all of the mark points are in amount n, are in number n. So now, if you expand again this guy, you get 3g minus 3 times the h0 by the Euler characteristic, because you can see that this is basically the Euler characteristic, and minus 3 times h1 plus 3 times h1. So you just simplify these guys, but of course the graph is connected, so this thing is 1. So you get 3g minus 3 times 1 plus n minus the cardinality of the edges. So now you get that the dimension of the stratum at the end of the day is just the dimension of the moduli space mg and bar, the bigger one we're after. And now you have a defect, and the defect has a very simple formula, it's just amount of edges. But this is exactly what we learned yesterday, because yesterday we saw that every edge corresponds to a node, and every node is the shadow of a limiting process where I took a loop and I degenerated it through a family of smooth curves limiting to a nodal curve. So every node was a lost dimension, and this Euler characteristic computation just confirms it. Okay, so in particular, this stratum has 1, 2, 3 nodes, and therefore has the codimension 3. Now, let me have a look at this natural maps. So the first thing I can do is what is called forgetful morphisms. So generally referred to as pi. It goes from mg n plus 1 bar to mg n bar. And what does it do? Then you just take a component with n plus 1 mark points, but since they're labeled and distinct, you know which one is the last one, the n plus first, and then you just forget about it. But somehow, if you think about it a bit, you'll see that you may run into troubles because forgetting a mark point is very easy, but somehow mark points keep the component stable. If you lose too many mark points, you may end up in an unstable situation, and now you want to worry about in exactly how many cases this can happen, and you want to cure these anomalies. So you want to define how the map should behave whenever you do end up with some unstable component. And if you think about it a bit, this can only occur in two possible ways. So the first way is when you have two stable components, let's say, and you have this component in the middle that has two nodes, so it's a separating component. If you remove it, then you would separate the graph. And you have the n plus first mark point exactly there. So this component only has two nodes and the end and the last mark point. So now if you forget about it, that's unstable. So you need to stabilize it. How do you stabilize it? Well, it's very easy. You just basically shrink the entire component to a point, and the two nodes get to coincide. And this is fine for dimensional reason because you forget the mark point, but you also forgot a node. So now the dimension is safe. And the only other case, well, I mean, if you have some other unstable components left and right, you can't, right? Because if either the component on the right or on the left would be unstable, and you contract this component, they will still be unstable afterwards, and they were unstable to begin with. So it's impossible. Like you need to have exactly instability only in the component in the middle where you have the n plus first mark point and nothing else. And the second case, the instability can occur is when you have a rational component again, of course, attached by a node to something else that can sort of extend to a graph that is complicated as you like, but it doesn't matter for us. So you just have a node with attached a rational component. This rational component have two mark points. One is the mark point you're forgetting, so the last mark point, n plus first, and the other one is just some other mark point with some label you don't care about. Now, if you're forgetting, so this component is barely stable, and as you forget the n plus first mark point, you get a rational component with two special points instead of three. So this is now unstable. You have a node and a label. And what can you do? Again, you shrink the component to a point, and you just end up with the label of the mark point there, and the node is gone. And this is again compatible with the dimension because you forgot about one mark point and you also forgot about a node. Okay, so those are the only two bad cases, and this is how to cure this instability. You just shrink the unstable component, and this is well defined. Okay, and what else can you do? Well, you can just take two components or two stable graphs, and then you just select the points that you want to glue. For example, the last mark point of the first guy and the last mark point of the second guy. Let me call them n1 plus 1 and n2 plus 1. So those are the last mark points of each of these strata of curves. And I now decide that I want to glue these two mark points into a node. So I just take something that had genus G1 as a genus and G2 as a genus of the second component. And when I glue them, I will have that the genus of the glued locus of curves is just the sum of the genera. And now when I look at the mark points, I will have, again, the glued component, the glued stable graph, will just have the sum of the mark points of the first one and the mark points of the second one, but I will have two as defect because I needed a mark point in the first component and a mark point in the second component to be glued together to form a node, and therefore I lost two in terms of mark points. Okay. And but this is again compatible with the other characteristic if you think about it. And the only last thing that I can do is exactly the same, except that now I'm not gluing two mark points of different components or different stable graphs, but I'm gluing two mark points of the same component. So now I will trade two mark points for genus. Okay, I will create a node, but now of course, in the normalization of this curve, I end up with the initial guy. But now if I consider the desingularization to compute the arithmetic genus, I will end up with a surface that has one more genus. But in the Euler characteristic again, the genus has weight 2 because the formula is 2g minus 2 plus n. So every genus has weight 2 and every mark point has weight 1. So if you think about it, you're trading two mark points for one genus so that they have the same value in terms of the Euler characteristic again. So these three maps are the natural maps of moduli space of curves, stable curves, and they are referred to as tautological maps. So whenever you hear tautological maps and tautological rings and so on, they have to do with these three maps over here. So basically, you're just either forgetting a mark point or you're gluing. But remember that when you glue, you can glue in two different ways. You can either glue two disconnected things, or you can glue the same thing. Okay. Maybe this is a good time to stop, by the way, because I talked for basically 50 minutes. Okay, so welcome to the second part of the second session. And we had a look at these topological maps. We can either forget a mark point or we can glue two loci of curves along mark points in two possible ways. Either we glue two things that were disconnected or we glue two mark points of the same component. Okay. And so now we also introduce this concept of universal curve. What is the universal curve? You can think of MGN bar as your moduli space of stable curves. And every point there represents an equivalence class up to isomorphism of your stable curves. And now the universal curve is that curve that actually tells you which curve it is, not just the point representing curve, but the actual curve. And for example, here there is this drawing that was designed by Dimitri Tsonkin that I like very much. And it tells you that if you consider the generic point in the moduli space, you will get something smooth, of course. But now if you consider this divisor, so this first orange one, this divisor, you will, let's say that this is the divisor that splits your smooth curve into two components by node. And now you have this other divisor that instead is shrinking a loop on a B cycle, so you give you this pinch. So now if you self-intersect this guy, you'll get two pinches. And here the generic point of the divisor would have just one pinch. But now you can also intersect the divisor that splits the component into two by a node and the divisor that splits by inserting one of these pinch. And so at the intersection, you'll have both of these features. So of course, this is codimension 2, and the other ones are codimension 1. So you can play these fun games, and also, I mean, there's a proposition that the universal curve, this CGN bar, is just isomorphic as family of curves on this MGN plus 1, because it's the same logic as before when we computed M04 and M04 bar. We parameterized M04 with this point T that was roaming around the curve, and by roaming around the curve was also parameterizing the whole space of possible curves. And it's the same thing here. You have this +1. So this extra mark points is roaming around the curve in all possible way. And roaming around the curve is just describing the entire curve by spanning the curve somehow, by assuming all possible positions in the curve. Very good. And then Every point of the curve can be seen as the forgotten mark points with two special cases. On the mark points, you have a bubble with the mark point, and on the nodes, the bubble with both nodes. So these are exactly the two cases that we've seen before. These two cases in which you have an unstable component that gets shrunk. And so with this trick, you can actually prove that the universal curve MGN bar is the same as MG n plus 1 bar. Okay, let us now talk a little bit about the cohomology of this space and the intersection theory. So when you take a differential form on U over G of an orbifold that has an action of a finite group G, you want differential forms on these orbifolds to be just G invariant differential forms on U. So this is how you define differential forms of an orbifold. They just have to be G invariant. And now when you're integrating over this space where you have this G action, now this is exactly the same thing as integrating the differential form that is also defined on U, just on U. But now you weight this integral by the inverse of the automorphism. So by the inverse of the cardinality of G, and because G is finite, this is a number, and so there are no problems. And also compact orbifolds have Poincare duality. So now you can take the pairing between the cohomology and the homology, and then you can just project on your field. Let's take the rational numbers as field through the integral. And this is a very nice source of cohomology. I mean, this is a very nice result that you can use for computations. For example, you can take any locus of curves that is identified by some stable graph, gamma, that we've seen before. And this is an element, it's a locus of curves, so it's an element in the homology. But you can always take the Poincare dual of a locus of curves, and that would identify for you an element in the cohomology of MGN bar. So you already know how to create a lot of cohomology classes on MGN bar. And of course, if the dimension is identified by, dimension is the total dimension minus the number of nodes, or equivalently the number of edges of the stable graph, then this is the codimension for you, the number of edges. Now, when you take the Poincare dual of that, it's clear that the number of edges identify the cohomological degree. So this is a very handy tool. You just send the codimension in homology to the degree as cohomology form. And also another thing that you can do is to take these Chern classes that you probably saw in the course, I assume, I'm not sure. So this ith Chern class would take a complex vector bundle of a certain rank R. And it's a topological invariant that would associate some cohomology element in the group, in the even cohomology. And this cohomology is in principle in the range from the 0th group to the rth group. So it goes all the way, it goes from constants all the way to the rank of the bundle. But then if you look at its component in the cohomological degree, which divided by 2 is higher than the rank, you would always find 0. So it just vanishes afterwards. So you have some canonical way through these Chern classes to associate two bundles cohomology classes, and then you have some control over the degree given by the rank of the bundle. And naively speaking, this guy would be given by, how many, the index I would stands for the number of linearly independent sections of the bundle that you need. Okay. So let me give an example. If you have some holomorphic line bundle, and you take some meromorphic section, you can take any meromorphic section, then you can define that S to be the divisor of zeros and poles of the section S. And so if X is a curve, for example, ZS would just be the sum over all the zeros with their multiplicity minus the sum of all the poles with their multiplicity. And then if you take the first Chern class of this line bundle over X, then you get just the Poincare dual of ZS. So basically, you just need to know zeros and poles with their multiplicity, and that would define for you. So this divisor would identify for you a homology class in the top, so in the dimension of X minus 2, and therefore, by Poincare duality, would give you an element in the second cohomology group of X. Okay, very good. And of course, it's a non-trivial result, the fact that you can pick any meromorphic section. I mean, it's just topological, so just if you change the meromorphic section, the cohomology class would be the same. This is a non-trivial fact, but we have a result that is ensuring us this. Okay, then if you take trivial line bundles, they have never vanishing holomorphic sections. So this ZS would be empty, and therefore you find 0. And so you can, naively speaking, think that these Chern classes measure how non-trivial a bundle is. And this kth Chern class of E, you can look at the singular locus of, well, you would take number of sections that is the rank minus k plus 1, and then evaluate it at some point and look for how many of them are linearly. I mean, maybe I don't want to go through. I don't want to go too much in details on this because I think that if you have a course in complex and Riemann geometry, you may as well just see this in more details, and I may cause some more confusion than something helpful. Let us go into something that is more concerning modular space of curves. In homology, we have this just the intersection. So if you take an element of the pth homology of X, where X, you can think that it will later become our modular space of curves, times the qth homology group, you can intersect them into something that lies in the p plus q minus dimension of X group. And now this would correspond in a cohomology to something that goes from the pth cohomology group times the qth cohomology group. And now you take this wedge product and you go to this p plus q cohomology group. And now this allows to compute many expressions of the form. For example, if you're integrating over X and you're intersecting the K1 Chern class of some bundle E1, and then you keep intersecting up to the KS Chern class of the bundle ES. Now, if you want to perform this computation in cohomology, you can always take the Poincare dual on each of them. And so now you can define this as a weighted number of points in the intersection of the class of M1, the class of M2 up to the class of MS, where Mi is just the Poincare dual of the Ki Chern class. And weighted number means that you take your points, but now on each point you have the action of a finite group, and weighted means that you always divide by the cardinality of that group. And now this will return a number if the degree of the class matches the dimension of the space. So we've seen that the kth Chern class gives you an element in the kth or in the 2kth cohomology group of X. And so now you want that the dimension of X is equal to the sum of these degrees Ki. All in that case, you have a chance to get a non-zero number. If instead the sum of the Ki's is too small or too large, so it's not exactly the dimension of X, you will just get 0 as a result. So, and one I wrote is singular. You can think of it as a singular locus of R1. So this first, the rank of E1, minus K1 plus 1 generic sections of E1. So this is how you can think about it, but probably you've seen, well, maybe you spent several lectures on Chern classes, so I don't want to take the shortcuts, you know. And you have that the wedge of Poincare duals is just the intersection of the Poincare dual and the intersection of the Poincare dual. So if you're integrating over some other space, it's just the intersection of the two spaces. Okay, so this was general, let's say, for some manifold, and also, I mean, some orbifold you just weight by the inverse of the group that is acting. But now let's apply this machinery to our case. So let us speak about which natural cohomology classes we have on moduli space of curves. So which bundle are we interested in taking? We are interested in taking this relative cotangent bundle. Maybe there is somebody that is not muted or somebody that is asking a question. I cannot really say. Anyways, you can take this relative cotangent bundle. So it's just a complex line bundle on the universal curve, CGN bar. And now you're removing the nodes. And the sections, what are the sections to this cotangent guy? The sections restricted to the fibers of the projection on of the universal curve over MGN bar are just differential one forms. And so with differential one forms, everything it's easy because if we want to take the first Chern class, we saw that it's just the locus of zeros minus the locus of poles. So it's the divisor of zero minus poles with the multiplicity. So now I mean, it's very easy to define it when you're excluding the nodes, so the singular curves on the open. And now if you want to extend this definition on the nodes, you have to do something. So if you have a curve with a node, you know that the nodes are just parameterized by this equation x times y equal to 0 locally. And you can see them as limits, as we saw yesterday, of nodes of the form x times y is equal to some parameter t, and now you send this t equal to you're sending it in the limit to 0. And what you can do is now you take the equation x times y equal to one of these parameters, and you have several of them. And along the fibers, what you have is that the differential d of xy divided by xy restricted to the fibers should be 0. But now this is also dx plus dy. Sorry, dx over x plus dy over y restricted to the fibers. And that tells you that basically, if you take the residue of dx over x, you'll get 1. And if you take the residue of dy over y, you'll get 1. But because they have to be 0, when you sum them up, it means that they need to be one the opposite of the other. So now you get the condition that you just need simple poles at the nodes, and moreover that the residues should be one the opposite of the other. So you get a space of sections of L is generated by these two meromorphic conforms. So just dx over x and dy over y. But now you need to add the condition that dx over x plus dy over y is 0. And that means that you can allow yourself simple poles at the nodes, but the residues should be opposite. So this is also how you extend, if you heard this already, holomorphic differentials to abelian differentials. So this is how you can deal with nodes on the open sets. So when you only have smooth curves, they would just be holomorphic. And then at the nodes, you just allow a little bit of poles, just simple poles with opposite residues. That would be enough. Okay. And then the age 0 of this holomorphic line bundles on C. But now with this trick, we'll just give you the space of holomorphic one form of C if C is smooth, or the space of these abelian differentials on C if C is nodal. So again, by abelian differentials, I mean meromorphic differentials, meromorphic one forms. At the nodes, you only have simple poles and opposite residues. And as example, you can consider, I'll give you an example in genus 1, you can consider this family of omega epsilon. So that it's an entire family depending on epsilon. They lie in the age 0 of this line bundle, but restricted to the fiber. And for every epsilon greater than 0, they will give you something that is singular, and in the limit, they will give you something that is non-singular, and in the limits, it will be singular. And they are given by this formula. You take some constant c, which is not 0, times dx, and you divide by the square root of x minus 1 and x squared minus epsilon squared. So that would give you x minus epsilon and x plus epsilon. And now you define the elliptic curve depending on the parameter epsilon as y squared equal to x minus 1 and x squared minus epsilon squared. And now you can check that the residue of omega epsilon at epsilon equal to 0 is just plus or minus c. And so basically I drew below what happens to this family of curves. Have that epsilon, you can take it as the length of this loop, as always. And now you have a holomorphic differential one form on the family, on each of these curves, on the family of curves. And in the limits, you will get that the residue on one side of the node is plus c, and on the other side is minus c. And you only have simple poles, of course. So that would give you at the node z plus and z minus opposite residues. And so that qualifies as a non-trivial abelian differential on a genus 1 curve. And yeah, so this is an example that we have. You can also try to write down in differentials like that in higher genus, but it's again, I mean, it's harder and harder. So another one of our protagonists is given by the holomorphic vector bundle of this holomorphic differentials. So that is usually referred to as E, and is called the Hodge bundle. And so basically, what is this guy? If you restrict to the fiber at the curve C, EC would just be isomorphic to the H0 group of L, but restricted to the fiber. So it's just a dimensional, it's just a G-dimensional vector bundle of holomorphic differentials. And so its rank is, of course, G, because the fiber is G-dimensional. And now you have the right to take its Chern classes from the 0th one up to the Gth one, because we know that after the Gth one, everything will vanish. So it's not interesting. So you can now define this differential, this element in the cohomology that you called lambda I. So lambda I is just the ith Chern class of the Hodge bundle E. And if you want, you can also take a polynomial in those classes. So you just define big lambda of U to be just the formal sum from I that goes from 0 to G of U to the power I. So U is your variable, and lambda I is just the ith Chern class of the Hodge bundle. So this is going to be quite an important protagonist for us. So again, you consider over MGN bar the Hodge bundle. The Hodge bundle is the bundle of rank G whose fiber is just the G-dimensional vector space of holomorphic differentials on the curve C. So it's a very familiar object, has rank G, and now you take all of its Chern classes. So lambda I will be an element of the 2ith cohomology group of MGN bar. And now I want to take the formal polynomial in U, in the variable U, whose coefficients are cohomology elements, this lambda I. And this object was studied by several people, and in particular, Mumford in '83 gave a beautiful, beautiful formula for this lambda, this big lambda. And just so turns out that lambda evaluated at 1, so if you plug u, if you substitute a variable u with the value 1, it's just the inverse of the class lambda, where u is substituted with the value -1. So if you take the product between these two lambdas at -1 and at 1, you just get a fundamental class. And this is an extremely strong condition, because it means that you are annihilating all of the lambda classes in this polynomial in a non-trivial way, because the fundamental class, it's of course in the 0th cohomology group, and so that there's just a constant. And so that means that all of this cohomology that you had in both polynomials, they just take each other out. They just simplify in a very non-trivial way. So this is just a corollary of Mumford formula. So you see there are pretty interesting results. The point is that Mumford formula states that this big lambda is an exponential of something very specific. But because it's an exponential, it's automatically invertible, because now you can take the exponential of minus the same thing. That will give you the inverse. So then when you multiply them, you'll get the fundamental class out of that. And the fact that it's exponential comes from the application of this Grothendieck-Riemann theorem. And because of that, you get this Todd class. If you're familiar, you get plenty of these Bernoulli numbers appearing, because when you apply the theorem, basically you multiply by the generating series of these Bernoulli numbers. Okay, so what are the other nice classes that we can consider? We saw at the beginning of the first slides yesterday that we had this Witten conjecture and this Kontsevich theorem, and they were about these building blocks of the cohomology that we call the psi classes. So now, finally, I can tell you what psi classes are. So if you consider MGN bar, you have, you want to define a psi 1 up to psi n. So you have one of these psis per mark point. And how do you define psi I? You can just take this cotangent line bundle, if you remember. But now you have these n sections. What do? They just go from, there are sections of the universal curve that basically point at the point pi. So you have S1, S2, S3 up to Sn. And they will just take a curve C with mark points P1, Pn, and we just associate the point pi to it. Okay. So now basically you're taking the cotangent bundle at the point pi of the curve. This is what you're doing, really. And now you allow pi to move around in the moduli space, but you always care about the cotangent space of the curve at the point pi. And now you're taking the first Chern class of this bundle. And now this is what you want to define as psi I. So psi I will live in the second cohomology group of MGN bar. So these are very, very important guys, and are the main protagonist of this Witten-Kontsevich story. The main reason why you want to consider tangent bundles and not cotangent bundles is that you want the result of the intersection to be positive. So you don't want these minus signs roaming around all the time. And the last protagonist of our cohomology is those kappa classes. Kappa classes are just pushed forward along the forgetful map of the psi classes. So how do you do? You take the psi classes, the psi class on the last mark point. So let us say that we are on MG n+1. So we have this last mark point labeled n+1. And we are going to forget about it. But before we forget about it, we consider the first Chern class on the cotangent space of that point that we're going to forget. This is the psi class of the point n+1. Now we're going to take powers of this psi class. We're going to take m+1 powers of this guy. So this is an element that lies in the cohomology group 2m plus 2, because it's just double. Each of them is in the second group. So if you take the m plus 1 power, that will lie in the 2m plus 2 cohomology group. But now we're going to take the push forward along the forgetful map. So we're going to forget the last mark point. And because mgn plus 1 as a moduli space has one more complex dimension than mgn, this map will also lower the dimension in cohomology by 2. So that's why we took the exponent of this class. We took the exponent m plus 1, because now that we're going to forget about the last mark point, we're decreasing the dimension by 2, and we will end up in something that we call kappa m that will sit in the H2m group. So this is the reason behind the shift of the indices. So now you have these protagonists, which are these psi classes. They have one complex degree, if you like. Kappa m has complex degree m, and lambda j has complex degree j. And then you also have all of these loci of curves given by stable graphs, and their complex degree is just given by the amount of edges, if you remember. These are the main protagonists of the cohomology of MGM bar. In fact, the cohomology of MGM bar is very, very large and ill-behaved. So people generally consider a subring of this called the tautological subring. And the tautological subring still contains all of the protagonists that we've seen. Okay, so just as a reminder of what we've done in the first slides of yesterday, we consider this Witten-Koncevich potential. This Witten-Koncevich potential is just the generating series of all the integrals of psi classes. So you can just take the integral of MGM bar, and then you take psi 1 to the power kappa 1, k1, psi 2 to the power k2, up to psi n to the power kn. And then you just encapsulate them in a generating series where you use some times t, k1, tk2, tk3, and so on to keep track of the powers of psi classes that you used. And then you want to sum over all the g and all the n and take 1 over n factorial by because of symmetry. It's not so important, but you have this generating series. And now you can compute the first terms. How do you compute the first terms? Well, let's try to compute some intersection numbers. So if I consider the integral over m0 3 bar of psi 1 to the power 2, well, this is of course 0, because m0 3, we know it's a point, has dimension 0. So I cannot take any positive power of psi classes. I cannot integrate 1. So that's going to be 0. The only non-trivial integral over m0 3 bar is going to be psi to the power 0. So it's just going to be 1. And this is the integral of 1 over a point, and that's 1. So that's why when you look here in the expansion, you will have like t0 to the power 3, and the coefficient of that would be 1. So there's this one that is invisible here is just this one because of this integral. And you're not going to have any other pure powers of t0 because I mean, you can have them, or you have m04, then you need to integrate something. I mean, then the next guy that you're going to have is this t1. This t1, what is the coefficient of t1? The coefficient of t1 will be psi 1 to the power 1. So psi 1 to the power 1 is something that lives in space of n equal to 1. And because it has degree 1 in cohomology, we need to find a space that has dimension 1 as a moduli space. And of course, that forces us to take the genus as 1. So we call that M11 bar, has dimension, as we saw, it was this Christmas sock, and in particular has complex dimension 1. But we can also retrieve the same formula with 3g minus 3 plus n. So if you plug in the numbers, 3g, when g is equal to 1 is just 3, minus 3 is 0, plus n equal to 1 is 1. And indeed, you have psi 1 to the power of 1. So now the degree match the dimension. So dimension 1 and degree 1, complex degree. Okay, so now this number is 1 over 24. 1 over 24 appears many, many times in many contexts in enumerative geometry, in enumerative algebraic geometry, string theory, and so on. And in fact, you have like two ways to compute this, which are a little bit long. So I wish I could go into the details of the computation. There is, I mean, you find, for example, you find a proof using Kontsevich graphs on the book of Enach or in the original paper of Kontsevich. Or in my paper on combinatorial Teichmüller space with many collaborators. Or you can find this, in fact, 3 different proofs via quasi-modular forms, depending on which modular form you're using. And that's in the notes of Zwonkin, which I also recommend. So very nice proofs, but to compute the fact that, to compute this integral here. Okay. So what about these integrals of psi classes? How do I compute them in general? Is there a general formula? Is there a closed formula? And the point is that there exist closed formula and a lot of tricks, like recursion, geometric tricks, combinatorial counting, and so on. But when we say closed formula, we have to be a little bit more specific about what we mean, because I mean, closed formula, I would say they only exist, in fact, in like genus 0 and genus 1, really. And the other ones would be, I mean, you can call them closed formula if you want, but there would still be some over partitions, over permutations. And, well, they are still like very complicated formulas. There's one version by Okunkov, there is one version by Buryak, and they have been shown to be equivalent directly. I mean, you do have some formula, but that you can plug into a computer and obtain an answer, of course. And you do have a lot of recursions, but somehow they're not like very simple closed formula. There will still be some over some objects that kind of explode with G and N that becomes big. That's what I mean. Okay. And then another thing that we have is this Virasoro constraints by Dijkgraaf, Verlinde, Verlinde. And they were shown to be equivalent to the solution of the Witten conjectures by Kontsevich. So for every m that is greater or equal to -1, you have these operators Lm, and they would annihilate this operator exponent of G. Well, what is G compared to F? Remember that F is just this Witten-Kontsevich potential. So it's the generating series that is encoding all of the intersections between psi classes. And now what is G? Well, just G is obtained by F, except that every time that you see a time tk, you're substituting P, the P variable, with an odd index. So 2k plus 1. And you also multiply by this prefactor 2k minus 1 double factorial. And so you take F to be the generating series of the psi classes integrals. Then you take G to be the scaling of F. Then you take the exponential of G. And then you build these LMs to be the difference between these A operators and these B operators, where the A operators just multiply by a P variable if K is positive, if the index is positive, or they're taking the derivative of a P variable if K is negative. And then these B operators, instead, they are quadratic in the A's, but in a certain way. And then after you build these LMs operators, they all annihilate the exponential of the Witten-Kontsevich potential. And moreover, they commute very nicely in the operators that out of all the possible commutations, they have precisely the commutation of the Virasoro algebra. So this is a very, very special thing. So meaning that if you take Lm and Ln and you commute them, they would result into the operator L m plus n, but only whenever then you have a delta on the indices. So basically, most of them would commute, except for just very few of them. Okay, and if you want to have some practice with this as an exercise, I would suggest to derive all the equations explicitly, meaning that you start taking some m, which is very, very small. You start from m equal to -1. Then after you're done with the exercise, you compute m equal to 0, then m equal to 1, and then m equal to 2, and so on. And what you can do is to take the integral 2m plus 3 double factorial times the integral of mg n plus 1 bar of psi 1 to the d1, psi n to the dn, and then you take psi last, attached to the last mark point to the power n plus 1. And then you express it as sums of products of integrals over mg prime and prime, where g prime and n prime are such that 2g prime minus 2 plus n prime is smaller than 2g minus 2 plus n plus 1. And you find the solution in the very last pages of the Zvonkin Introduction to Modular Spaces notes. So if you want to check the solution of the exercise after you're done, you can just go there. And I actually wrote down the first two equations of this exercise. So the solution for m equal to -1 and m equal to 0. They are very beautiful and they're very useful. And you see here when m is equal to -1, you have -1 plus 1, that is 0. And also twice -1 is -1 plus 3 is 1. 1 double factorial is 1, so it doesn't appear. And here you have that basically the trick is when you have psi to the power 0 on a mark point and you're forgetting about it, you're getting something over mgn bar. And now, because the sum of all of these di's is, of course, 3g minus 3 plus n plus 1. Now, since you're integrating over mgn bar, you want the sum of the psi classes to be matching the dimension again. But now the dimension is 1 smaller. So you need to decrease in some way these guys. But you cannot decrease it in a non-symmetric way because they wouldn't make sense to prefer some psi classes to some other. So now you're decreasing one of the indices by 1, and you're summing over all possible ways of doing that with the condition that if you had 0 already, and now you're trying to decrease 0, then you wouldn't have that summand because the psi class to the -1 would vanish. That's the convention that you're going to use. And now the dilaton equation, instead, if you had a power 1 here instead of power 0, now when you're pushing forward, you would get what? You get the kappa class, because kappa classes are just push forward of psi classes, if you remember. That's something that we've seen here in the definition of kappa classes. No? Now, if I take m to be 0, I have psi to the power 1, and I will get kappa, I will get, say, k0. But k0 is giving you the Euler characteristic of the surface. And so you will get a factor of 2g minus 2 plus n times this guy. And as an exercise, I would recommend to try to compute these numbers. So for example, the integral of psi 1 to the power 3 over m0 6 bar. And for example, psi 1 to the power 2 times psi 2, or the integral of psi 1, psi 2, and psi 3, or the integral of psi 1, psi 2 over m1 2 bar, or this guy. And basically, by computing these examples, I mean, it's very nice the first time you do it, because then it's what makes you realize that string and dilaton equation are extremely useful. And because here you only have, I mean, here you always have some power of psi class that is either 0 or 1. And therefore, you can always use psi, either string or dilaton equation to make them simpler. So you just turn these integrals into simpler integrals until there's one that you recognize that you computed before, or you keep going until you get the trivial one. So all of these exercises can be done by using string and the Latam equation, and by using the fact that integral over m03 bar of 1, so you're integrating over a point, this is just 1, and the integral of psi1 over m11 bar is 1 over 24. This is something that I would love to prove, but it would take me some time. So especially, I mean, the quasi-modular forms, maybe not so much, but the Kontsevich graph, which is a very nice proof, would take me some time. As an additional exercise, you can prove, that's very nice, that if you have a computation in genus 0 or in genus 1 of an integral of psi classes, that it's always achievable with Dilaton and string equation and this initial data. So the genus 0 and the genus 1 case are completely determined by string and Dilaton equation. And these two initial data. Whereas for genus 2 or higher, you need also the other real-cell constraints. And then I would just recommend to check your answer with the software I talked about earlier yesterday. So you just can go on every any electronic sheet of calculus that you prefer. You can use, for example, CoCalc and go on the cocalc.com website, and because it's completely free. But if you have it installed or if you use some other platform, it doesn't matter. And then you just open a Jupyter notebook and you select the Sage Math Engine, and then you can just import ADM cycles. So I just wrote the Sage lines that you need to write. And then you can, as I said yesterday, you can look at the initial reference on ADM cycles and read the syntax there and which functions you have to compute these kind of psi classes integrals. But as an experiment, you can just say that GNN is equal to 1, 1. And then you take the psi class 1 GN, meaning psi 1 over the space with genus G and n mark points. And then you use the dot evaluate function to get the result, and the result will be 1 over 24. And then you can play with it. Of course, just make sure that the total power of psi classes is the right one for the G and N that you're using, and you should be able to get the numbers that you want in low genus and low N.